Good evening, everyone. In our last class, we have been talking about the basic principles of atomic optical spectrometry. Over there, we have discussed that this atomic optical spectroscopy, it basically deals with the what you call signals which are being generated from the atoms. So within the atoms, how the signals are generated? Within the atoms, we have seen that there are electrons which move from either from the ground state to the higher state or vice versa. And accordingly, what happens is that if the electron is coming from the higher state to the lower state, so higher virtual state to ground state, then we can see the emission spectrum. And if and during this phase, when it is coming from the virtual state to the ground state, it emits light. Okay. On the contrary, when we talk about the absorption spectrum, herein the electrons within the atom, they gain some energy from the white light which is being made incident onto the atoms, and it goes to the high energy state and it absorbs the light, and due to that we obtain a dark band. So we also discussed that the lambda emission and lambda absorption, both of them, they occur at same wavelength. And this provides us information about the quantum energy levels. Okay, and then we have seen into the what you call the emission spectra of different different atoms. Okay. Then we had discussed about the basic components of the analytical techniques which are based upon the atomic optical spectrometry, and we have discussed that there are three types of spectrometric techniques. One is atomic absorption spectrometry, one is atomic fluorescence spectrometry, and the last one is atomic emission spectrometry. So we have discussed the basic principles. This is the implementation technique methodologies of the atomic emission, atomic absorption, and the atomic solution spectroscopic devices. Then we have discussed about this AAS and AES. These two are most commonly used atomic optical spectroscopic methods. Atomic fluorescence spectroscopy, it is not very commonly used in elemental analysis, but they are also there. And in the atomic absorption spectroscopy, we have told that the background will be brighter, whereas the absorption peaks, they will appear as the darker regions. Whereas in the atomic absorption, atomic emission spectroscopy, we will get some bright peaks over a black background. Then we have talked about two types of atomic absorption spectrometric devices. The first one is the single beam spectrometer, sorry, and the second is the double beam spectrometer. Then we have also talked about the different types of radiation sources, and we have seen that there are broadly two types of radiation sources. One is the line source, and the other is the this continuous source. Now, among the various type of radiation sources, the commercial this atomic absorption spectroscopes, they usually have these hollow cathode lamps. Okay, so we will discuss over here about the hollow cathode lamp, what is the construction and the functioning of the hollow cathode lamp. So if you see over here, we have two electrodes. One is the anode and the other is the cathode. And as the name suggests, hollow cathode lamp. So hollow cathode. Herein we have a cup-shaped cathode. Okay, so which is hollow in between. So it is just like a one-sided open channel. Okay, so that's why the name comes from there, the hollow cathode. Okay, so the voltage applied over here is usually 500 to 1000 volts. Okay, and in some machines you will find that a voltage of approximately 300 volts can also be applied over here. It depends upon the manufacturer who designs this kind of lamps or the machines. Right now, this electrode system, it is being enclosed within a glass enclosure, and at the tip over here where I am marking this red, we have a quartz window. Okay, so it is expected, so whatever the light will be generated, that will be generated within this glass enclosure, they are expected to move out of this quartz window, and they will gain entry into the spectrometer. Okay, now this glass enclosure, as the name suggests, it is an enclosed area. um, it has a very low pressure, which comes out to be in the range of 1 to 5 torr, and it is filled with either neon or argon gas. Okay, now what happens is that when we apply such a high voltage over here in between the anode and the cathode, so what happens, this anode, which is made up of the tungsten, mm, this thing, this tungsten element, so what happens, due to the application of this high voltage between this short space, the gas, the buffer gas which is present over here, so say for example the neon, so neon, it becomes neon positive plus this negative. Okay, electrons are being generated. Now this anode, it is positively charged, so what will happen, this electron, it will move into the anode towards the tungsten element, whereas the neon positive charge, it will go and it will strike within the hollow cathode, because it is positively charged and our cathode is, it is negatively charged, so it will be accelerated, these neon positive ions, they will be accelerated over towards the cathode, and while they are being accelerated and they are hitting the cathode, from here the metal excited form of the metal, they come out. Okay, so this metal, they are getting out of this hollow cathode layer. Okay, now these metals which are being created, as I showed you, I am showing it with a dark circle over here. That means this metal atom, it is in a high energy state, and as it comes out over here, it loses its energy and it comes to its ground state, and during the conversion from the high energy state to the ground state, it emits light, and this light, it would be the spectral lines what we have seen. So in this case, suppose if I have to analyze sodium ion in a solution, suppose I give you a pond water and I ask you to find out sodium ions over here, so what you will be doing, you have to use the sodium hollow cathode lamp. If I ask you to find out this potassium, then you have to use potassium hollow cathode lamp, and so on. So why this is so? This is because if you go back to our first slide, herein if you see, what we have said, the quantum energy levels in both the cases are same. So we have also discussed, so when we want the absorption to take place, the absorption will only take place when we are exciting the atom with the what you call emission wavelength light. Then only it will happen. Then only the absorption will happen. Otherwise, it will not happen. Okay. So this is why if I have to analyze the sodium ions, I need to use sodium hollow cathode lamp. Okay. Now, when it is coming from the excited state to the ground state, it will emit the light in specific line spectrums. And in general, the line spectrum which is being radiated from the sodium cathode, it is at around 589 nanometer. Now, this 589 nanometer wavelength light, it comes out of this window and it enters into the sample layer, and then we have the detector, we have the spectrum analyzer and the detectors, and they do the measurement. So what happens is that if the sodium concentration is low in the solution, the absorption of this light, it will be lower, whereas as the concentration of the sodium ion it increases, the concentration the absorption of the light which is being emitted by the sodium hollow cathode lamp, it will be increasing in a concentration dependent manner. Okay. Now, in hollow cathode lamps, we have a conduction which happens at a lower voltage and with more current. This is in contradiction to the cold cathode lamp that does not have a hollow cathode. Okay. Then sputtering. What is sputtering? The sputtering is the ionized buffer gas ions when they are accelerated towards the cathode, that results in the sputtering of the atoms from the cathode. So when we have applied such a high gas, I have said that there is an ionization of the gaseous molecules, and these gaseous molecule, charged gaseous molecule, when they are accelerated towards this hollow cathode, and then they what you call, they result in the release of charged metal atoms from the hollow cathode. This process is called this sputtering. Okay. Now, line source LSAS, why it is used? It is used because we get the characteristic radiations. Okay. So as for example, as I told you, for sodium ion, we need radiation at 589 nanometer. Then only there will be an excitation of this metal ions, metal atoms. Okay. So how it will be generated? It can only be generated if we use a line source, or which will be able, which is having, or which is being generated from the sodium cathodes. Okay. In other words, when we use this sodium hollow cathode lamp, we need to be sure that we are analyzing only the sodium atoms. Okay. So here we have the characteristic radiation. So characteristic radiation from the sodium hollow cathode lamp will be able to excite this sodium atoms. Now, if you see in a atomic absorption spectrometer, you have a number of hollow cathode lamps. Why? This is because in the previous slide I told you that if I am using a sodium hollow cathode lamp, then I will be able to analyze only sodium ions. If I use potassium hollow cathode lamp, I will only be able to use I will only be able to analyze potassium atoms, right? So because of this, we need a number of hollow cathode lamps so that we can analyze different atoms. So analysis of different atoms would need different hollow cathode lamps. This is one of the important things. Okay, so this is the thing. So if you see, there are a number of hollow cathode lamps which will be there. If you see in this picture, you can see 1, 2, 3, then 4. So likewise, you have at least 5 to 8 hollow cathode lamps, and uh, these are basically this can be replaced easily. So depending upon which elements you want to use, you want to analyze, or the which atoms you want to analyze, you will be requiring only those hollow cathode lamps. Suppose if you just have the requirement to analyze 2 atoms, then you take just 2 hollow cathode lamps and you place it over there. So atomizers, these atomizers, they are the heart of any atomic optical spectrometry. Okay, so if you have a bad quality atomizer, then your analysis um, will not be that good. Okay, so there are different types of atomizers. Okay, so the different types of atomizers, they include the flame atomizers, which is basically a continuous atomizer. Then we have electrothermal atomizers, which is basically a discrete atomizer. Then we have low discharge atomization, hydride atomization, and cold vapor atomization. However, under normal circumstances, flame atomizers and electrothermal atomizers, they are mostly used. In flame atomizers, what happens? Suppose you have a flame, and within this flame you put in the samples in the spray format. The samples are there, and then over there the solvent, the volatilization happens, and the atoms are being excited over there. Okay, so flame atomizers, it can also be of different types. So depending upon the fuel what you are using, the first one is air acetylene flame. Herein we have we can achieve temperatures up to nearly 2300 degrees centigrade, and then we have nitrous oxide into a acetylene flame. Okay, so this nitrous oxide acetylene flame, it gives us a more reducing environment as compared to the acetylene flame. Okay, so if there is any samples which are prone to oxidation, then this nitrous oxide acetylene flame, they can be used for the analysis. Okay, yeah, if you see nitrous oxide system, it offers higher reducing environment and is suited for analytes with high affinity to oxygen. Okay, now the different steps in continuous atomization. So you have the sample solution. Okay, now this sample solution, uh, it is being nebulized. Okay, and during this nebulization form, you get some droplets. Okay. Now after this droplet, you have the desolvation process. Desolvation means you are removing the solvent. Solvent is being removed. Okay. Now when the solvent is being removed, it forms dry aerosol. It is just like powder. So this is a dry powder like stuff, but these are very fine dry powder. Okay. And after that, due to the heat you are being generated, so how you are generating the heat? We are basically generating the heat by flame. Okay. So since we are heating these dry powders within the flame, then we are due to this we are having the volatilization process, and during this volatilization we get the free atoms. Okay. So the purpose of the atomization step is to convert the analyte to a reproducible amount of gaseous atoms that appropriately represent the sample. Okay. Sample atomization limits the accuracy, precision, and limit of detection of the analytical instrument. Okay. So this is of important thing. As I told you, this the atomization process, it is the heart of the atomic optical spectroscopy. The better is the quality of your atomizer, the better will be your accuracy, the better will be the precision, and better will be your limit of detection. So the step what I have told over here to you, that the sample they have to be in the solution form. So what happens if you have a sample which is in the solid form? Okay, for solid form, what happens is that we have laser ablation method. Okay, so in this laser ablation method, suppose you have a solid over here and you make a laser beam of high intensity incident onto the sample, and due to the incident high intensity laser source, the samples over here are directly heated and they are being atomized. So there is no need for such a long process in laser ablation method. So in laser ablation method, we basically convert a solid sample directly into the gaseous atoms. Okay. Now coming to the working of the flame atomizer, how do they work? So in your class 11-12 lecture, you must have studied about this Bernoulli's theorem. So in this Bernoulli's theorem, what you have, if you see, if you have a capillary over here and you have an open source, say P2V2, and over here you have another capillary. So let us take this in this fashion, in a simplified fashion. Okay. Okay. So it is in the open here, P2V2. Over here we have P1V1. Now if we start to squeeze the bulb, so what will happen? There will be an increase in the velocity of the air. You can also blow air from here by different other methods. If you do not have a squeeze bulb, you can blow the air into the tubing through your mouth also. So in that case, so V1 will be increased, so correspondingly the pressure will decrease. P1 will decrease. Okay, so the P1 over here and P1 over here is same. So the P2 is increasing. So since the P2 is increasing, it will put more and more pressure onto the liquid, and the liquid, it will climb up into the capillary, and from here, due to the high velocity, they will be taken out of this nozzle, and as this liquid is coming out of this nozzle, it forms droplets. Okay, so it is one of the very easy way of nebulization. It is one of the easy way for nebulization. So over here, then what happens? So this process is used to create the droplets of the samples. Okay. Now, if you see over here, this is a basic schematic diagram of a flame atomizer. So it is basically a total consumption burner type atomizer. So you have the inlet 1 and inlet 2. So in inlet 1 and inlet 2, what you have, if you go back, in one thing we are having the air and the other thing is the fuel. Okay. Similarly, over here, if you want to modify the environment, we have nitrous oxide and acetylene. So acetylene is again the fuel. So in one of the inlets, you will be either using the air and the air or the nitrous oxide, and in the other inlet, we will be having the acetylene. Okay. In the inlet 1, we will be having air or nitrous oxide. Whereas in the inlet 2, we will be having the fuel. Now, when this air is coming over here through this, it is going towards the nozzle. Okay, and at the same time, if you see, we have a sample introductory capillary. So due to this pumping action, which we have just discussed through the Bernoulli's theorem, so through that mechanism, the sample, it is being inserted and it is being pushed towards this flame. So there are two types of flame. And just at the tip, we are having the primary flame. At the outside thing, we have the secondary flame. And this dark color blue, it is called the internal flame. While taking the reading, what we do is that we do not take the reading from the primary flame region or from the secondary flame region. In the secondary flame region, this light color, this thing, it is highly oxidative in nature. Because this flame, this outer flame, it is in contact with the air, external air, which is full of, which is having a large source of oxygen. Due to this reason, uh, the atoms, they may easily get oxidized in this outer region, and hence while taking the reading, a conscious effort is being made such that the reading is not taken from the secondary flame. The reading is taken from the internal flame, wherein it is expected that complete combustion of fuel has taken place. And to this reason, it is expected that in the internal flame region, we will be having stable atoms which are completely atomized. Stable atoms which are completely atomized. Hence, the readings are being taken from the internal flame region. Okay. Now, this type of atomizer can be easily developed and they can be widely used in various laboratories. However, as I told you, when these drops of samples are being formed through this type of atomizer, what happens? There are certain larger droplets, as I told you before, and there are certain smaller droplets. So the flame that is being produced, many a times it is an unstable flame. Okay, so you may get some noises over here. The signal to noise ratio, it will not be much high. Okay, so in the case of flame atomizer, we may not have a very good signal to noise ratio. Now, how to avoid this condition such that these large droplets, they do not gain entry into the flame region? So to avoid that, this premix burner type flame atomizer, they are being used. So if you see over here, we have the sample entry capillary, we have the nebulizer unit, we have this nebulizer oxidant unit, we have the auxiliary oxidant if you want to put in another oxidant into the system. Okay, so you have the fuel system. So all of this you are having over here. Okay, now after this, what happens is that we have a system called flow spoiler. Okay, now what this flow spoiler does is that, say for example, you have three inlets, say for example, inlet 1, 2, 3. One is for the oxidant layer, oxidant like air or nitrous oxide, right? Second is for fuel, third is for sample. Yeah, there is another output over here which is called drain. Now, herein what will happen is that this flow spoiler, they are present. Now what is happening? You are having these droplets over here. Now the flow of the oxidant and the these samples, they are how they have to move? They have to cross these baffles. They have to cross this baffle to gain entry over here. So again, from here it will gain entry over here, right? So what is happening over here? So it is not following a straight path. The samples, the nebulized samples, the droplets which are being formed, they are not able to follow a straight path. In fact, there is a zigzag path over here. So due to this zigzag path, so what happens is that the fine mist, they can gain entry over here. They can gain entry at this burner head. This is the burner head. Over here we are having the burner head. Okay. So over there we will be having the flame like this. So at this burner head we will be having only the droplets which are fine. Fine means they are smaller in shape. So herein we get a very stable flame. However, there is a problem over here. So only if only the fine mists they are gaining entry into the burner head, then a large amount of the sample is also being lost, and it is being lost through the drain. And if the sample is lost, then what happens? You are losing your accuracy. Okay. So to compensate this, what happens is that if you see in the flame, in the first type of total consumption burner, we are using a very small part of the flame for the analysis. Herein, if you say, if you have this thing over here, this flame is there, we use a large window path length to capture as much information as possible. That means whatever this rectangular box I have drawn, the light will be passed through this rectangular box like window. Okay, so in this way you are able to capture as much information as possible from the atoms which have been atomized. Okay, and in this way we artificially increase the signal to noise ratio for the analysis of the atoms over here. So do you have any question for me? Anyone has any difficulty up to this in understanding? So herein I have given you different uh, compositions of oxidants, fuels, and up to what temperature we can go, and what is the maximum burning velocity within that range. So we are not interested over here. In this last column you may forget it. However, the understanding of this oxidant, fuel, and temperature, it is needed for you. I may give you that there is one sample which needs to be excited at say 3100 degree centigrade. So which oxidant and fuel you will be using. So you need to understand, you need to memorize this oxidant, fuel, and temperature things. Okay. So over here, another important thing, if you are giving oxygen, that means the burning will be happening in a much more oxidative environment. Then when you use air, the concentration of oxygen will be much lower as compared to the oxygen itself. So the oxidation rate will be much lower. And in the last case, in the nitrous oxide, the oxidation of the sample atoms, it will be much lower. Okay, because this nitrous oxide, it helps to provide a reducing environment. Now coming to the graphite too. So this is basically an electrothermal atomizer. So over here we basically use a typical tube, and usually it is graphite tube. So in this graphite tube, if you see, there is a hollow part over here, and it is basically a small it is a hollow cavity, and we have an opening from there. And this port, it is basically a sample inlet port. So this graphite tube, it is being put into the electrothermal atomizer over here, if you see. So we have gas, and then since we are electrically heating the graphite tube, so we need to keep it cool. So to maintain the temperature, we have a water jacket over here like this, and then we have removable window. Through this window we have to put the sample through injectors into the graphite tube. Okay, so then they are being heated out, and after being heated, what happens, we pass the light from one end and we measure the light intensity or the light spectrum at the other end. Okay, so in this way the electrothermal atomizer it works. Okay, the main advantage over here is that you do not need this other kind of say oxidants or fuels. So we can, this can handle both liquid and solid samples. Okay. Points to consider: flame atomization is the most reproducible of all the liquid sample analysis. Okay. However, the flame atomization has lower sensitivity than the electrothermal atomization, as oxides are easily formed, which leads to reduced absorbance of the samples. Okay. Then samples could be drained as waste and therefore have a low residue, low residence time, leading to low efficiency. Okay. And lastly, this is for basically for this premix burner. Premix burner flame atomizer. And lastly, the flame fluctuations can affect the absorbance of the samples. Okay. Now, lastly, we have the ICPAES, which we discussed, inductively coupled plasma atomic emission spectroscopy. Okay, so we have this aqueous dissolved solvent. So we have the pump, and then we have this argon gas which comes in. So this argon gas, it is used both as a carrier, nebulizing gas element, and also as the carrier gas. So this argon gas is being used using this nebulizer. So through this pump, continuously the dissolved sample, it is being put into the nebulizer, and this argon gas which is coming into the nebulizer, it is passing the sample through a very small hole, and we are getting this droplets. Okay, now the larger droplets, they are being removed through this drain. Okay, and the fine mist, they gain entry into this chamber, and in this chamber we basically generate plasma. Okay, so how do we generate the plasma? We generate the plasma using the RF power supply, and this chamber, it is called torch. Okay, and it is made up of silicon oxide. Okay, so over here the argon is carrying out, and it is carrying the what you call this mist in this direction, and due to the RF power supply over here, it is creating a very high voltage over within the area, and due to that high area, a plasma is created, and from this plasma, which is a very, what is a plasma? Plasma is nothing but it is a very high temperature zone. Okay, and from this high temperature zone, the elements, they get excited, and then when they try to come down to the ground state, they emit light, and then we have the detectors, and since it is in the 90-degree position, it is called the radial positioning of the detector. Okay, so in this way we have this ICP AES, inductively coupled plasma AES construction. Okay. Next, we can have the data acquisition system in the axial position also in a similar environment. However, in this case, we use we can also use, instead of the liquid sample, we can also use the solid sample, as I told you previously. So we keep the solid sample over there. Where we keep it? We keep it in the ablation cell, and in this ablation cell, we have this argon gas which is purging this chamber, this ablation cell, and we use 266 nanometer wavelength based wavelength laser, which is based on ND-YAG laser. Okay, so after the atoms or the samples are being atomized, this argon gas, it takes the atoms into this plasma. Okay, and then we have this ICPAES detectors which are in the axial position, and then the signal are being captured and we go for the data acquisition. So it is called laser ablation for atomization slash inductively coupled plasma AES. So why we call it as laser ablation for atomization? Because we are atomizing the samples over here. Okay, and here why ICPOES? Because we use inductively coupled plasma for generating the atomic emission spectroscopy. Okay, uh, as I told you before also, that using this flame technique, either you can go for atomic emission spectroscopy or you can go for atomic absorption spectroscopy. In emission spectroscopy, you will just need a detector. Okay, whereas in atomic absorption spectroscopy, you will be needing, in between you will be having this plane, so you will be having the source, and on the other side you will be having the detector. Okay, so this is the difference between this AES and AF, and all the other stuff it remains the same. And in the case of atomic fluorescence spectroscopy, this source would be at 90-degree angle. So with this I complete the chapter. So I hope every one of you have understood, right? And do you have any questions?
No, sir.
Okay.